One Africa TV's WhatsApp on 081-200-6659 or send an SMS to 555. One Africa TV, it just gets better.
ShopRite's birthday for more low prices. Like 2 liters Right Brand sunflower seed oil, only $44.99. And 2 liters Nami orange squash, just $22.99. Go Wololo with our more low price birthday.
The same applies to boiling points. Usually melting and boiling points follow same trends, similar trends in elements. So since the melting points become lower and lower down the group, the same trend will apply to the boiling points. And indeed, look at this. Lithium boils at 1,330 degrees Celsius. Then sodium a little bit lower, and then potassium a little bit lower and lower and lower as we go down the group again. So the same trend applies to the boiling points. They decrease, they go down as we go down the group. So this arrow shows the higher, where is the higher value and where is the lower. We see that lithium has a higher boiling point, and francium should have the lowest, even if we don't know exactly the value. Now let us go to the density of these elements. The density, as shown by this arrow, becomes higher and higher, increases as we go down the group. So lithium has the lowest density because it is on top, the first row, the first period of these elements. Lithium, then look at this density, it's 530 kilograms per cubic meters. If we compare with water, water has a density of 1,000 kilograms per cubic meter. These are the SI units, density. So if we can compare with water, look at this density of lithium. It's only 530 kilograms per cubic meters. That's nearly half the density of water. Sodium is at 970, which is also less than the density of water. Then we go to potassium, less again, rubidium and cesium and so on. So we see that the density increases as we go down the group. And look at these first 3 elements, lithium, sodium, and potassium. All of them have densities which are less than the density of water. There's a little bit of a discrepancy here, some anomaly in the densities, but overall we see that the density increases as we go down the group. And the first 3 elements, lithium, sodium, and potassium, have densities less than water, which means if we put a chunk of lithium or sodium or potassium in water, they will float in water because they have less density. Anything with less density than water floats on top of the water. That means if they are solids. If they are liquids, they can also float, provided that they don't mix with water. So these 3 metals, the top 3 of the alkali metals, float in water. They are so, in other words, they are quite light. I mean, if we have similar chunks of inside of the 3 metals, they are quite light relative to water. And in fact, the lithium, look at this, its density is so small that it even floats even in oil. And oil is less dense than water. We know from experience that oil floats in water. And lithium floats even on top of on oil, despite the fact that they are metals and they are solids. They float. All right. So these are, let us summarize again about these properties. They are very, very reactive metals. They are all metals. I don't know if I said that at the beginning. They're all metals. In fact, most elements in the periodic table are metals. And they have all the common metallic properties. Shiny, they have this metallic luster, and so on. But they are very reactive, and the reactivity increases down as we go down the group. The melting and boiling points decrease as we go down the group, and the density increases as we go down the group. But the top three metals, especially, as they have such small densities, which are smaller than water, so they float in water. Okay, what else can we say when looking on this table? Let's see here. Here we have some pictures. Here's lithium, and as we can see, this is oil here, and we can see that lithium actually floats in oil. And here we have sodium metal to see how shiny it is, because it is a metal and it has the metallic luster which is characteristic of metals. All of them, as you can see, they do look like metals. And here is potassium, which is stored in oil. In fact, all of these are stored in oil because if we leave them open in the air, they react with the oxygen in the air because they are very reactive. And because they react, they become dull and dark very fast because they are covered with metallic oxide. They're covered with an oxide very fast. And we don't see the metallic luster because they react so quickly with the oxygen in the air. And what else is here? Lithium, sodium, and potassium are so light that they actually float in water. Yes, they float. All of these first three float in water, but lithium floats in oil, even in oil. Here we have it. We see it floating in oil. That's enough. And this picture here shows rubidium and cesium, which are alkali metals, which we find at the bottom of the alkali group here in the periodic table. Where was it? Here we are. You see the rubidium and the cesium in periods 5 and 6 further down, and they have such a low, their melting point of rubidium and cesium. Look at this. For rubidium is 39 degrees Celsius, and for cesium is 28 degrees Celsius, which means if it's a very hot day in summer, the cesium, for example, will become liquid. It doesn't stay solid. And even rubidium, 39, well, some countries have summers which heat the 40 degrees Celsius, very hot. Then the rubidium will also melt, and it will be liquid rather than solid. And here we have these two metals, rubidium and cesium. Both here it's in the liquid phase. Obviously, if we raise the temperature, they become liquid very easily. So, but we can see the color, the shininess, this metallic luster, which is rubidium is kind of silvery, has a silvery color, and cesium has like close to the goldenish color, a pale gold color. Now, as far as the reactivity is concerned, let's talk a little bit about the chemical properties. And then I want to show you a video. Trend in the reactivity of the alkali metals, in other words, of the group 1 elements. Trend in the reactivity with water. When they all react with water very easily, so metal means the alkali metal plus water, they give a metal, they change to metal hydroxide, which is a chemical reaction, and they also emit hydrogen, and therefore, when we place them in water, we see a big fizz. We'll see in the video. And sometimes, because there is a lot of energy released from the reaction, the hydrogen catches up fire, so we end up having fires and explosions, and sometimes it can become quite dangerous. So, as we go down the group, we said they are more, the reactivity increases. They react more and more violently with water or whatever else, with whatever else they react. But we're talking about water in particular here. So when we see lithium reacting with water, we see, if we place a little bit of a chunk of lithium in glass of water, we're going to see it zooming around on the surface like a madman. It may ignite, even might catch fire. If we place sodium in water, it will zoom around like a madman, and it will ignite and might even blow up. Of course, it depends how big is our chunk, okay? But as we go down the group, they react more and more violently. Potassium, it says, will blow your head off. Well, if you put a big chunk, of course. Rubidium will blow your neighbor's head off. Cesium, take a wild guess. And then francium, yeah, okay, this, of course, it will be a humongous explosion, but fortunately, this is so rare that we don't find it at all easily. It's actually very rare. We cannot have it in an ordinary lab. But nevertheless, as we go down the group, the reactions with water become more and more violent, and with elements further down the group, things are becoming really, really dangerous. So that even with the top metals, if we are at school, for example, and we put a piece of sodium in water, the teacher has to put a tiny bit of a piece of sodium. Otherwise, if we put a big piece of sodium, it would be a big disaster. So somebody needs to know what they do when they demonstrate these activities. So let me find now this video, this YouTube video. Okay, here it is. Let's make it big. Okay.
6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a light flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our 5th alkali metal.
Okay. So the video was not very clear, but it gives an idea. I hope you could hear it properly. So in the meantime, I was reading at your messages here. Yes, the group 1 and group 2 elements, let's go back to the periodic table, the alkali metals, which we're discussing now, and also the second group that we're going to talk a little bit soon. Yeah, they are metals. They are metals. They exhibit all the physical characteristics of metals, and they behave like metals. they have characteristic chemical properties of metals. They are metals. But because the alkali group have elements have just one electron in the outer energy shell, it's very easy to give it away and bond with other elements, and that is why they are so reactive. They are so reactive that we really we do not find them by themselves easily, because they react with other elements and they form compounds. But they are metals. And the same applies to the group 2 elements, the alkaline earth metals. They have quite similar properties because they are so easy to react. So here were the reactivity with water that we saw just now. And yeah, it's nice to know that the reason why the alkali metals are so reactive is because they only have, if you remember, we discussed it last week, the outer energy level has just one electron. Because the previous energy level is complete with 8 electrons. So the last one goes to the outer energy level and it's only one. And because it is just one, it's easy for this, the atoms of these elements to give it away to some other element, some other atom of some other element, to bond together to become more stable, because elements are more stable if they have complete outer energy levels. So it's easy to give one electron and become stable with a complete energy level, the one that stays behind. And that is why they are so reactive. And the same we can say about the group 2 metals, the alkaline earth metals. Let's discuss a little bit about the alkaline metals, not in detail, because it's quite similar. What we are going to say is very similar to the group 1 elements. And why the similarity? Because the alkaline earth metals, being members of group 2, here it is, these ones have 2 electrons in their outer energy level. These ones, the group 1 has just 1, but the group 2 have 2 electrons in the outer energy level. And 2 electrons is also easy to give away, to bond with other elements and become more stable. That is why they are also very reactive, and the reactivity also increases as we go down the group. So, but we can talk about this group 2 because there are some certain elements like calcium and magnesium which are very useful. And in fact, calcium and magnesium are very useful in our living organisms, because these are these important trace elements that our bodies and systems do need in order to be healthy and live a healthy life. Calcium, for example, as we know, calcium is a very important element that we find in our bones and teeth, and we need to drink our milk and our dairy products to get our calcium. I mean, it's such an important element for our skeletons, and not only for living organisms. And magnesium too is very important, a very important element that we need to take. But nevertheless, so the group 2 elements are also very useful and also very reactive. And because they are very reactive, we don't find them as elements in our surroundings, in nature, because they are always bound to some other elements, and they are found in compounds. And in fact, we find them very common to find them in the form of their oxides, like magnesium oxide or calcium oxide and so on. Calcium oxide, for example, which is so common, we call it a lime. In fact, in the past, because it's so common to find them in locked in compounds, especially their oxides used to be called alkaline earths. And the early scientists, before Mendeleev and from the 17th century before, people thought that the alkaline earths were actually the elements. They didn't know that they were actually compounds of a metal plus oxygen. They thought these were the elements because it was quite hard to separate them. They were very heat resistant, these alkaline earths, as they used to be called, and they were not dissolved in water. So a name for this type of substances that were non-metallic substance that did not dissolve in water, and it was resistant to heating, this type of substances, they used to call them alkaline. They used to call them earths, actually. They used to call them earths. And this is where the name of these metals comes from, the alkaline earths. It was only in the 18th century, at some time, when chemists realized that the alkaline earths are not elements on their own, they are compounds, and they can be broken down to elements in like metals and oxygen. And therefore, the name alkaline earth metals get their name because the initial understanding was the alkaline earths were the elements on their own. So anyway, so we still keep the name alkaline earth metals. And why alkaline? Because eventually, if we place them in, if we manage to dissolve them in water, they form alkaline solutions. And the hydroxides, for example, are alkaline. And the same applies to the alkali metals of the group 1. The reason why they're called alkali is because they form solutions which are alkaline. The oxides and hydroxides are alkaline. The same with the group 2 elements. And that's all we can say about this group. It's not necessary to say anything more, so because the time is gone now. Next week, I think we need to talk now, to discuss a little bit about the properties and characteristics of the group 7, the halogens, and the group 8, which are the noble gases, also two very, very important groups. And we're going to see that these halogens in group 7 react very easily with the group 1 and group 2 elements, and we're going to see why. Okay, guys. So thank you very much, and next week we'll continue with the periodic table with 2 more interesting groups, as we said. Okay, so enjoy your week and keep well. Now we'll continue with certain groups from the periodic table, the very important groups. Last week, remember, we discussed group 1 and group 2, the alkali metals and the alkaline earth metals, all of them metals, except for the hydrogen. But the alkali metals, we assume they start from lithium and below. And we said that they are very reactive, and their reactivity increases as we go down the group. And why are they so reactive? Because they only have 1 or 2 electrons in the outer energy shell. The alkali, which are group 1, have 1 electron in the outer energy shell. And the group 2, the alkaline earths, have 2. That is why they belong to group 2. And because they are very few electrons, 1 or 2 are very few electrons, it's easy for them to give them away to some other atom, to join with another atom during a reaction, and that is why they're very reactive. It's easy for them to give away their outer electrons. Now we're going to go for a big jump, and we go to the group 7 or group 17, the new numbering. This is group 7 with the Roman numerals, or 17, which is the numbering, the modern numbering of the periodic table. So this is group 7, we can say. Let's call it 7 now. And this group, we call it the halogens. Here is where we find the halogens. All of these are the halogens. So which ones are the? We start from fluorine. You see here fluorine, bromine, iodine, astatine, and tennessine. Okay, this last one, tennessine, we are going to ignore it completely because these are from the elements that we manufacture in the lab. They don't really we cannot really find them in nature. So they are so rare, and their properties are not very well understood yet. Astatine, we knew astatine, but still it's quite rare, and it's also radioactive, and we're also going to ignore it for that reason. And it is possible that because due to its position from the periodic table, as we can see, it might not even be a non-metal like the others above, which are the main, the primary, the important halogens. This one could be like a semiconductor, could have such properties sometimes. And we don't know much about this either. But we are going to focus a lot on these 4, which are the most important halogens and truly very, very important elements, because they react easily. They are very reactive, and they play a big role in the compounds that we find in nature. They're a big part of them. So here is these are the elements that we're going to focus: fluorine, chlorine, bromine, and iodine. Yeah. Many people call iodine as well as iodine, like the others: fluorine, chlorine, bromine, iodine. But apparently, the proper name for this element is iodine. It's the only one that ends in "ine." All the others end in "ine." If you remember, you can call it iodine. Otherwise, you can call it iodine, and it's okay. It's not the end of the world. All right. So these are the halogens we are going to focus on. And let us look at some properties of them. Since we would expect them to have very similar properties, since they are all part of the same group. Remember, elements that we find in the same group have very, very similar properties. And in fact, Dmitry Mendeleev, when he produced his the first proper periodic table on which the modern periodic table is based, has placed these elements one under the other because of their properties. Then they didn't know about electrons and about energy levels. They could see properties, and they could figure out that similar properties, there must be something common among these elements.
When you're saying things that degrade women, for me, number one, I am not there, because that is basically what I don't believe in. I don't stand for things that degrade women.
What do you think we can add? What can we put in the basket? First of all, let's put Blossom back in the basket.
Look at the person like, man, let's do a song.
Let's do something.
Just
let's
like
collaborate.
Let's collaborate.
Americans were claiming us.
Yes, exactly. To the rest of the world, they belong to us. Namibia, Baba, Namibia.
I'll help you carry on.
Creating music and putting some stuff out for the people who've been supporting me, that's definitely something that's next on my list.
Accommodation is the ability of the eye to focus on distant and near objects, and I bring it in contact with the electroscope. What you must keep in mind is positive charge can't move. It is the negative charge that moves.
So the first one, EF, is then going to be 0 minus negative 2 over 4 minus negative 4. Look at my signs. If you go wrong there, if you don't substitute in brackets, you're definitely going to get wrong answers.